let's say I had the reaction where I had some copper ions. They have a positive charge of 2, and it's in an aqueous solution. There could be some other negative ions in that solution. Actually, we could talk about that in a little bit. But we know that when you have these ions in solution, they all disassociate. So you just have to know you have a bunch of ions just floating around in water. There could be some other negative ones to neutralize the entire solution. But let's just worry about the positive ones for now. And in that solution, I'm going to put a bar of zinc. I'm going to put a bar of zinc. And what happens is that they essentially switch places. Is that the copper wants to jump out of your aqueous solution. I should probably draw this. So let me actually let me draw it. So let me have this is my solution. And in my solution, let me make it blue because it's aqueous, so most of it is water. I have some copper molecules here in the solution. They're +2 charge, +2 charge. I could have some other ions that are negative, like some nitrate ions or whatever, but they're all disassociated and they're all mixing around with the water molecules that are polar, and that's why ions disassociate, or salts in general disassociate well in water. And I stick a bar of zinc in it, solid zinc. So let me do that. So I stick a bar of solid zinc into it. And so what this reaction says is that these copper ions, if they can get a hold of some electrons, and essentially become neutral, they would rather go back into the solid state. And the molecules of zinc out here that are in the solid state, if they can lose some electrons, they want to jump into the solution. So let me write down the whole reaction. So if the copper can get some electrons, they're going to go into the solid state. Copper will go into the solid state. And if the zinc can lose some of electrons, they'll become positive ions or cations. And then they will go into the solution. I'll do the same color. Plus zinc +2 aqueous. And actually, just so a little side note here, these are actual ions. We've been dealing with oxidation numbers, and when you want to know the oxidation number of an ion, the oxidation number is the same thing as its charge because it's no longer hypothetical. Remember, oxidation numbers were hypothetical charges if a bond were ionic. In this case, they are ionic, so the oxidation state or the oxidation number is the same as the charge. And just as a side note, the convention, if it's written 2+, this means that this is a real charge. If it's written +2, at least this is the way I learned it, maybe there's different conventions in different places, then it would be an oxidation state, which says, oh, it's not necessarily an ion, but this is what it would be if it was an ion. So if someone writes +2, this is oxidation state. If they write 2+, they say, hey, this is a real charge. And likewise, if you just have a regular ion that has like a charge of 1, so let's say you have Na+, this means that it's an actual charge. If you wanted to write its oxidation state, you would write +1. Small little note. It doesn't probably make a big difference in the whole scheme of things, but sometimes it can get confusing whether something is an oxidation state or an ion. But depending on where you're going to school and what your teachers or conventions are, you might want to clarify that and just make sure that they use the same conventions that at least I remember when I first learned it. So anyway, let's go back to this reaction that's happening here. So let's do the half reactions for this. So we start here, and actually we can just look at the oxidation states to begin with. This guy has an oxidation, he has a charge of 2, which is also an oxidation number of 2, and he goes to a neutral charge. So clearly he gains 2 electrons, which means that he was reduced. He went from a positive charge to a 0 oxidation state or charge, so his charge was reduced. So let me write that. So this guy was reduced. And let me write his half reaction. He started off with some copper in the aqueous state, and he got 2 electrons. That's how you get reduced. So plus 2 electrons, and he ended up in the solid state of copper, and his oxidation number is now 0. Now let's see what happened to the zinc. The zinc, and it starts completely neutral in the solid state, no extra electrons or deficiency of electrons. But then once he jumps into the solution, and once the zinc jumps into the solution here, he has a charge. So he must have lost electrons. So the half reaction for zinc, in this situation, you have zinc as a solid, and he reacts to produce two electrons, and then be left with just a and then he's in the water, and he's now an ion. So let me put that there, an aqueous solution. So if we did this experiment right here, and I will tell you right now, this reaction moves forward. This is truly a reaction. We're going to talk about in a second how badly do the electrons essentially want to jump from, where are they jumping from? They're jumping from the zinc to the copper. So we're going to talk a little bit about how strongly they want to jump and the voltage. And voltage is really just how badly does charge want to move, or how much potential energy does charge have. But this whole reaction, you just have to think about what's happening is that you have charge moving from, as the zinc jumps into the water, as the zinc jumps into the aqueous solution, it's passing on some charge to the copper that jumps into the solid form. So electrons are moving. Electrons are moving here. And if somehow we could harness these moving electrons, we could create a current. In this situation, it's all chemical. The electrons are moving around, but they're not doing it in any organized way because the solution is all mixed up. But this is an interesting situation we're dealing here. And we can even talk about how badly the electrons want to move in these directions. You can look at these half reactions, and you can look it up in a table, and you can get these energies or the voltages for these reactions. And this half reaction right here has a voltage. So they'll sometimes write E. Sometimes it's an E naught right over there. But that's kind of out of the scope of at least a first-year chemistry course. But they'll say it's 0.34 volts. And then this reaction in this direction has a potential difference. The energy is 0.76 volts. If I wrote this in the other way, if I wrote this reaction of zinc plus 2 electrons going to zinc solid, then you would just switch the sign. But what this says is that this state right here, is a higher energy than that state. So it wants to go in that direction, and it wants to do that with an energy per coulomb. And you can watch the physics playlist on more details of volts, but volts units are joules per coulomb. This is how badly the electrons want to join the copper. That's the best way of viewing it. And this is a measure of how badly the electrons want to leave the zinc. So if you wanted to talk about this whole reaction, so this whole reaction that we have up here, we could say it's an energy. So the energy of this entire reaction up here, we know that electrons really want to join the copper with this energy, and they really want to leave the zinc with this energy. So the energy of this entire reaction, how badly do electrons want to move from zinc to copper to form this over there, is just the sum of the two. So you get what's 1.1 volts. And you're probably saying, hey, Sal, all this talk of volts, this is interesting, and current, is there some way that we could construct a battery or a galvanic cell? If you don't know what a galvanic cell is, it's what we're about to construct right now. And the answer is obviously yes, because that's the whole point of this video. So how can we somehow harness that charge? So let's separate the two reactions. Let's separate the two. So let me put my zinc bar here. And let me put I'll try to stay true to the colors that I used earlier. And let me put my copper bar there. Actually, maybe I should copy and paste what I wrote up here, just so we remember the reaction itself. Actually, yeah, let me do that. Never hurts. Okay. I'll paste it down here. You can ignore all the squiggly lines around it. And let me put both of my bars in some aqueous solution. And there could be some other dissolved ions in there to help neutralize the different. So I put them both in an aqueous solution. But they're separate. They're separate. And let me label them appropriately. So this is my zinc right here, bar of solid zinc. And this is my bar of solid copper. I should do it in a different color. So this is copper right here. my bar of solid copper, and then I have an aqueous solution. So what happens if we were to connect these two metals, right? They're metals. So if we look at the periodic table, they're both, depending how you call it, they're both transition metals. They both have the sea of electrons, so they both conduct electricity well. What happens if you connect these two with a wire? So if I connect them with a wire right here, like that, we already know that the zinc is just dying to jump into the water and lose its electrons, right? So let's say that that happens. So the zinc jumps into the aqueous solution, and it turns into a positive ion of zinc, and then its electrons are left behind, right? So it essentially has two electrons. I did the half reaction right here, right? The zinc jumps into the solution, and it leaves behind two electrons right here. So one electron, two electrons here. They really want to jump off of the zinc. Now, I have a lot of copper out here in the solution, that really want to jump onto this bar of copper, right? But right now, they're all ions. These are all +2 ions. These are all +2 ions. And they really want to jump onto the bar and join all of these other copper ions here. But in order to jump onto that, they have to get some electrons. Each of these guys have to grab 2 electrons. And we know the kind of the potential or the electromotive force with which they want to grab those electrons is 0.34 volts. Right? These guys want to jump here and grab electrons from someplace with plus 0.34 volts. These guys want to jump off of the bar and leave their electrons behind with 0.76 volts. So what do you think is going to happen if we have a conducting wire here? Well, those electrons are, once this zinc just jumps off, those electrons are going to travel through the wire. And then they're going to be available, because these are surplus electrons, to merge with these copper ions that want to jump back onto the bar. So these copper ions are going to jump back onto the bar. But from this reaction, what's happening? You're having a current flow. Current is actually flowing. And what is the voltage across this? How badly does an electron want to go from this zinc on this bar to over here join with some copper in the solution and let that copper join onto that bar? It wants to do it with plus 1.1 volts. Now, the question is, the electrons are flowing in that way. What is the cathode and what is the anode? So the cathode is the positive terminal of, well, since you can already imagine, this is a battery of sorts, right? Because we are able to generate a current by having a voltage difference across 2 terminals. The cathode is the positive terminal. It's the positive terminal. That's where the electrons want to go to. And then the anode, and you can familiarize yourself this with, just a cation is a positive ion, an anion is a negative ion. So the anode is a negative terminal. So what's the negative terminal here? The negative terminal is where the electrons come from. So the electrons are coming from these zincs jumping off. So here, this is your negative terminal. And what's the positive terminal? That's where the electrons want to go to. They want to go down here and be available for these coppers that want to jump out of the solution. So this is our positive. This is our positive terminal, or our cathode. This is the cathode. This is the anode. And if someone says, hey, does oxidation or reduction occur at the cathode or the anode? Well, what's occurring right here? We have zinc in its solid state right here. We have solid zinc jumping in, and it's neutral, and it jumps into the solution, and it leaves 2 electrons behind. So it's losing electrons. When you lose electrons, you're being oxidized. So this is where the oxidation is occurring. Likewise, on this side, you have copper ions that are already in the solution, and they are gaining electrons. So their charge is being reduced. So the cathode is where reduction is taking place. Reduction. Now, you're probably saying, oh, Sal, this is a nice, cute little, a battery, or this is called a galvanic cell that, you've created this current. But I see a problem here, because as this happens, you're going to have more and more positive zinc ions jump into the solution here. You have more and more positive zinc ions in here as this progresses. And you're going to have fewer and fewer copper ions in here. So if you assume that there were some other, let's say there was, maybe there was some, to keep this solution neutral, maybe, there was, the copper is positive, maybe you had some chloride in there, chloride anions that were keeping it, that were keeping this solution neutral, and maybe you had some chlorine anions here that were keeping that, well, it started negative, but then maybe it gets a little bit more neutral as the zinc jumps in. But once this happens a lot, then it becomes very positive, right? This is becoming more and more positive as more and more zinc jumps in, and this is becoming more and more negative as more copper jumps onto this bar. So what can we do to solve that problem? What they do is, and this is just one way to solve the problem, there's actually many, but this is probably what you might encounter in your first year chemistry class, is they create something called a salt bridge. A salt bridge. And what they do is they create a, I guess we could call it a pseudo-aqueous solution of a salt. Maybe it is, maybe it's potassium chloride, right? So in here we have potassium. Potassium has a plus charge. It's aqueous plus chlorine with a negative charge, aqueous. And I say pseudo-aqueous because it's not really super liquid water. What they do is they try to make it more viscous so it just doesn't mix completely. If this was pure water, then all of it would just fall into this solution, and you would really have nothing up here. It would be a useless device. But what they do is they create a gel out of this that's still aqueous enough that the ions can move around. The sodium and chloride ions can move around. So let's say that those are the sorry, not the sodium, the potassium. Let's say that's the potassium. And let's say the chlorine ions are, well, I already did it in that blue. So chlorine are the minus. And what happens is, as we have this oxidation reduction reaction that's causing these electrons to travel from the anode to the cathode, this becomes positive, this becomes negative. The salt bridge allows the negative components of the ionized salt, in this case the chlorine, to go into this solution to neutralize it. So they'll end up having more and more chlorine as the zinc pops off. So you can kind of, if you were to evaporate the solution, you'd end up with a bunch of zinc chloride. And on this side, to keep the balance here, you'll have a lot of the positive parts, components of the salt. So the sodium would jump in to replace the copper that's jumping out. So when you have this whole thing, it enables the current to keep flowing without having a bad effect on the charge. Because what happens if this becomes really positive? If this becomes really positive, I'll do it in a vibrant color because there's no salt bridge. At some point, the electrons are going to say, hey, I can either go over here and drive this reaction, or hey, I got a lot of positive stuff hanging out here. Maybe I don't want to leave at all. So you have to do something to neutralize the charge here. Likewise, if this becomes really negative from all of the chlorine atoms jumping out, electrons aren't going to want to go here because they, like charges, repel each other. So that's what having the salt bridge neutralizing the solution does for you. It keeps it from getting negative, and then our galvanic cell can keep operating.